All right, welcome back, everybody. Now it's my turn to go off script for just a minute. Alan thanked us, but we all would like to thank Alan. Alan DeLuna has been the chair of, or the lead of these tech sessions for several years. He has been, what you see us do is just kind of surrounding the event itself. He's doing all the lead up work to make all of this happen. Weeks and months of his time spent arranging all these session chairs, getting all these sessions reviewed, the posters, everything like that. And I will say that it's gotten better and better every year, even including this year, transitioning to a virtual environment. He does it as a lone soldier, but we support him as much as we can. And so we wholeheartedly thank Alan very, very much for all of his dedicated work to this. It's excellent stuff, and we truly, truly appreciate it. So one of the highlights of the year, and it's all due to Alan. So with that.
Thank you, Joe.
Absolutely, sir.
Voice from the darkness.
Yes, indeed. Okay, so with that, let's get into our next session. So this one is Earth observation and viewing. Our session chair is Narasimha Prasad. He is an aerospace technologist, and our session this time around includes 4 presentations. Here's a look at them now on your screen. So I'll give you a second to take a look at those. And as we get into this, what we'll do is we'll run through these presentations one by one right in a row, and then we'll have all our presenters come online live and to answer your questions. And to do that, please, please, please submit your questions using the question and answer tool down at the bottom of your screen. Send them in there, and we'll do our best to get to them. So with that, let's get started and roll the first presentation.
Hello, welcome to my talk today. I'm Timothy Lang from NASA Marshall Space Flight Center, and I'm going to talk to you about 3 years of the lightning imaging sensor on board the International Space Station. So ISS LIS is a product of a large number of people's hard work and a large number of organizations working together to get this sensor up to the space station and keep it running. There are too many people to name, but I do want to acknowledge all of their contributions. All right, what is ISS LIS? So ISS LIS is essentially a high-speed camera that images at 500 frames per second, and it looks at the 777 nanometer oxygen line. This line has a very strong lightning signal that actually exceeds the daytime solar signal and allows us to detect lightning during day and night with storm scale resolution, millisecond timing, and spatially uniform detection efficiency. Now, what is flying up on the ISS is actually the flight spare of the original LIS instrument that flew on the tropical rainfall measuring mission several years ago. So we took the flight spare out of mothballs, got it ready to put onto the ISS LIS and integrated it onto the SDP-H5 payload and launched it to the ISS back in 2017. The great advantage of ISS LIS relative to trim LIS is that it expands the latitudinal coverage from 38 degrees up to 55 degrees north and south. And this allows us to look at not only the tropics, but also much of the mid-latitude region. And you can see where relative to trim LIS, which is the bottom plot, ISS LIS, which is the top plot, provides increased coverage of Europe, northern United States and southern Canada, as well as northern China and other countries. And these have very strong lightning signals. So, but where they overlap between trim and ISS LIS, there's very good agreement. So we're still getting the same high quality lightning information that we got for several years with ISS LIS relative to TrimLIS. We have also been up there long enough with ISS LIS to resolve the seasonal cycle of lightning. And so in the plots below, you see essentially the movement of lightning poleward during the summer in the respective hemispheres, and then back towards the tropics during the wintertime of that particular hemisphere. Now, if you were looking closely at the other plots, it was pretty obvious that most of the lightning was occurring over the land versus the oceans, and that's seen here in the diurnally resolved plots that have been integrated over the globe. If you look at the red curve, it's the total lightning, and relative to the land signal, which is pretty much dominates, and then the oceans is just a small amount of lightning, and it's fairly constant throughout the day, whereas over the land it's observed in the afternoon. That's that top plot there, the local afternoon. So ISS LIS is still up there on the space station. We are part of the senior review process that all our science sensors go through, and we're hoping to pass through that. And if we do, we plan to move to a different part of the ISS to accommodate incoming instruments. But if we continue to operate, we're looking forward to integrating our data into the current and near future program of record, such as the GPM constellation, Meteosat third generation, which has a lightning imager, upcoming GOES instruments, and other instruments that are very complementary to ISS LIS. Thank you for listening.
Hello everyone, my name is Rafael Guzman. I'm the CTO of SATLANTIS, a company specialized in state-of-the-art imaging payloads for the new generation of microsatellites. In my talk, I showed you the results of our first space mission, the in-orbit demonstration of our camera iSIM 170 on board the International Space Station. As you saw in more detail in that talk, we have demonstrated our ability to provide sub-meter resolution from space. iSIM stands for Integrated Standard Imager for Microsatellites. As you can see here, iSIM is a binocular camera. Right now, both telescopes offer images only in the visible and near-infrared, but our final version will optimize the second telescope to operate in the short-wave infrared. So this will make iSIM the only camera in the market that can simultaneously observe from 450 nanometers to 1.7 microns with unparalleled spatial resolution. We have designed two different models of iSIM, a large model, iSIM 170, which is specifically designed for the new generation of large microsatellite platforms, and iSIM 90, which is ideally suited for the new generation of 12U and 16U CubeSat platforms. The flight model of iSIM 170 was successfully completed last year and sent to Japan in December 2019 for integration in the JAXA facilities of Tsukuba as part of the HDEV-9 mission. As you can see, iSIM 170 is a rather small camera, about 30 by 40 by 50 centimeters in size and with a total mass less than 15 kilos. The iSIM 170 version for this IoT is only panchromatic, since the main goal of this first mission is to validate our technology in space and demonstrate we can reach sub-meter spatial resolution. The final version of our iSIM 170 camera will offer sub-meter resolution in RGB, 2 meters in near-infrared and less than 4 meters in the shortwave infrared. Our camera was successfully launched from Tanegashima in May 21st this year as part of the JAXA HDEV-9 mission. The Konotori module docked with the ISS 5 days later, and in June 9th, ISS Commander Chris Cassidy installed our iSIM 170 camera through the airlock of the ISS and, using the robotic arm, positioned it on the outside platform of the Japanese Kibo module. Here you have an example of the images taken with our iSIM 170 camera on board the ISS. On the bottom of this slide, you can see a mosaic showing the Bay Area. We typically take mosaics like this with our iSIM 170 camera about 1,000 to 2,000 miles across with a 4 miles swath from the ISS. I'm going to use these images to illustrate the improvement in spatial resolution, signal-to-noise, and contrast after our super resolution technique and demonstrate our final images have sub-meter resolution. For instance, here you can see a zoomed-in section of the Treasure Island. The native resolution of these images is about 2 meters. This is before, and this is after our resolution technique. You can now clearly see the containers parked in this industrial area. We applied the same techniques to various examples of images. In particular, in my talk, you could see an airport near San Diego. After our super resolution technique, you can clearly resolve the stripes in the runway, which are a bit more than 3 feet apart. The airplanes are now seen in focus, and even you can distinguish the engines, and also you can easily resolve the blades of the helicopters, which are less than 3 feet wide. Thus, the final resolution of our iSIM 170 images from the ISS is below 1 meter. Before finishing this presentation, I would like to briefly mention the next mission we have already contracted. With the current IOD mission, we have been able to fully validate our super resolution technique. Our next project is Casper, selected by NASA and the Air Force Research Lab for the STP-H7 mission to the ISS, with an estimated launch date of September 2021. With Casper, we will be able to validate the other 2 key innovations, multi-spectrality without loss of spatial resolution and agility. These 3 key innovations define the main business niche for SATLANTIS, that is, the real-time monitoring of critical irregular linear structures on Earth, like coastlines, pipelines, or borders. Thank you.
Because of its ability to penetrate the canopy, LIDAR technology is often used for determining vegetation height. In agriculture, nearly all research has focused on high-resolution airborne LIDAR systems, but these systems are limited in their scale, often to a single field. The goal of this project is to determine the feasibility of using GEDI and ISAT-2, 2 spaceborne LIDAR systems used primarily for large area environmental studies, to determine the height of common agricultural crops. This would allow crop height to be measured on a continental scale and implemented into algorithms for predicting national crop yield. A simple methodology is presented. First, we'll visualize the GEDI and ISAT-2 returns over an agricultural area. Then, we'll use airborne data to determine canopy and ground elevations. Through comparison, we'll determine if the canopy and ground elevations that are shown in the airborne data, the high-resolution data, can also be distinguished in the spaceborne returns. GEDI is the first sensor. It is a near-infrared laser full-waveform LIDAR unit mounted to the International Space Station. GEDI uses full-waveform technology. This means that the reflected energy of a single laser pulse will be recorded as a signal and not a single point. When analyzing the waveform over a field, we expect that 2 peaks will be detected. The first peak will represent the canopy height, while the second will represent the ground, as illustrated in the graphic. Here are our findings for the GEDI experiment. So we're going to look at the return down here in the sorghum field, return number 42, and we can see in the graphic here that we have the amplitude of that GEDI return in red mapped against its corresponding elevation. And the first thing you'll notice is we predicted a bimodal distribution, and that's not what we see here. We see a Gaussian distribution. So we're not able to directly detect both the canopy elevation and the ground elevation from a single return. Now, when we compare that to our UAV data, we have the brown line here represents our ground elevation, and the blue line represents the canopy height elevation determined from high-resolution UAV data. We can see that the GEDI return does detect the top of the canopy, and that if we have an independent data set, such as this brown line, we can determine crop height, in this case 70 centimeters. Moving on to the next sensor, ISAT's ATLAS sensor is different from GEDI. It calculates an elevation based on time of flight every 70 centimeters along track. It does not produce a waveform like GEDI, rather it produces a dense string of discrete points. However, like GEDI, it is designed for global coverage. What are the expected results from ISAT-2? Well, since it produces discrete points, we will compare a profile instead of a single return. Over a field, we expect many returns recording the top of canopy, and a few returns that penetrate the ground and retrieve the ground elevation. Here are the results for the ISAT-2 test. We chose a swath that passed over a parking lot and a cornfield in Indiana. The red line that you can see here is Indiana State LIDAR returns for this profile. This represents our ground data. The blue returns are the ISAT-2 returns. We can see over the parking lot area that the blue dots and the red line match, showing that we're on the same vertical datum. And then as we pass over to the other end of the graph, over the cornfield, we can see that there are a few blue dots on the ground, meaning that ISAT has detected the ground, and many blue dots on the top of the canopy, meaning that ISAT has also detected the top of the canopy. So what's the conclusion? First, GEDI fails to directly indicate the height of shorter vegetation, such as crops. ISAT-2, however, can be used to determine the height of crops independent of other datasets. Future research will focus on first, can the GEDI distribution be used to infer the height of crops? Second, can we validate the heights that were derived from ISAT-2? And finally, we'd like to automate crop height determination over large areas.
Hi there. I'm Liam Kennedy, the founder and inventor of the ISS-ABOVE, and I'm here to present Life After HDEV, exploring the future of live HD video from the ISS. So yeah, the high definition Earth viewing HDEV experiment, this NASA experiment brought live views of the Earth from the ISS to the public from April 30th, 2014 up until July of 2019. So check out what those views look like. We're starting off with the camera platform had really three different camera views. This is showing the forward facing view actually as the space station was passing over Egypt, and that is the River Nile there winding along the left up to the center of the image there. And this was the Nadir camera. By the way, the place name that's appearing there is not on the original stream. That's added by my product, but I just wanted to explain that. And obviously this is lower quality than you would have seen. The video from HDEV was streaming out at 720p. And this is one of my favorite views, the rear camera, because we get to see some of the space station's structure there, showing Soyuz, a Progress, and a bit of a Cygnus spacecraft there. But you get the idea. These were an exceptional way to view the Earth from the international. So the video from HDEV was seen by more than 300 million people worldwide. Now that HDEV is gone, what is next for live HD video from space? Firstly, why should anyone care about that? So, why do I care about this? Well, I have a very particular connection with HDEV via my ISS-ABOVE device that's been sharing these views with students and the public in schools and science centers and private homes around the world. I thought I'd better just tell you a little bit about that in case you have never heard of the ISS-ABOVE. It's actually this little box that's in the top left corner there. It's actually a Raspberry Pi that you connect to a TV, projector, or HDMI, and it displays that live video from the ISS, but also includes lots of other information. And in particular, it references who's on the space station and tells you every time the International Space Station is passing you by, not just when it's visible. And it does this also in a very engaging way because it has a very bright LED that lights up every time that happens. So that is 5 to 8 times every single day. So it could be passing you by in the middle of the day, and when that was the case, you would see live video of you from space. So I've had this product out there since 2014, and now there's over 3,500 installed worldwide, lots of them in schools and science centers, and there's a whole set of lesson plans that were actually funded by a grant from the ISS National Lab. Thank you, ISS National Lab. So, as I mentioned, in this presentation, I'm going to share some of my own thoughts and really my adventures since 2015, really on my own personal journey to secure a future for live HD videos of the Earth from space. I will finish by saying thank you, and especially thank you to Carlos and Sue and Dylan and everyone else I know at Johnson Space Center. You've made this so much fun, and I couldn't have done any of this without your help. I really appreciate it.
Okay. Excellent stuff. Excellent stuff. I didn't know about. I didn't know about ISS above. That's fantastic. That is so cool. I was just sorry. I was distracted because I went to the ISS above site to look at it to see what it was all about. That's great. So as we're getting all of our folks in here, I wanted to remind everybody to submit your questions using the little Q&A button down the bottom of your screen. Please do that. We've got some great presentations here and they're ready and willing to take your questions, so please submit them. And with that, Prasad, I will turn it over to you. So take it away, please.
Do you hear me?
Yes, loud and clear.
Good afternoon. Welcome to Earth observation and viewing. This is the last but one session, and I hope so far the ISSR&D conference has provided a lot of good and very valuable information. And also I welcome the panel members who are very hardworking and excellent, as we see from their work that they are going to present or they have presented in the executive briefing. And I will introduce the panel members. The first one is Timothy Lang, and he is the new mission scientist for the Lightning Imaging Sensor on the International Space Station. He is a lead research aerospace technologist at NASA, NASA Marshall Space Flight Center, and his research interests include thunderstorms, lightning, precipitation, and winds. And the second presentation was titled Optical Payload Technology Demonstration on Board the ISS. And the talk was given by Rafael Guzman, and he has got his PhD from University of Durham, and he is now a professor at UF Department of Astronomy since 2001. And he is now a full professor since 2009 and the chair of the department again, I think till 2012. And he is the co-founder and CTO of SATLANTIS, and it is a spin-off of UF, and he is the CTO there since 2013. And his specialty is in galaxies and astronomical instrumentation, and he is the recipient of prestigious accolades from by Spain and US academia. And the third presentation was provided by Joshua Carpenter from Purdue University, And he's a registered professional surveyor from Ohio University, Ohio, and he's currently attending the Purdue University for PhD studies in geomatics engineering. And much of his industry work has focused on underground utility and tunnel mapping. And his research interests center on using emerging technologies to expand the capabilities of the infrastructure and resource mapping industries. Again, the last talk was given by Liam Kennedy, and he's the inventor of the ISS-ABOVE, a Raspberry Pi device displaying rich information and live views of the Earth from the ISS to schools, science centers around the world since 2014, as you heard. And again, ISS-ABOVE has a Space Act agreement with NASA, GSE for STEM outreach efforts, and is an ISSNL educational partner. Again, having said that, welcome all the panel members, and we will start the questions asked by the audience. The first question goes to the lightning sensor topic to Timothy. And Susan asks, is there any plan to take other measurements outside of the 777.4 nanometer, which is our oxygen line, to look for details within the lightning, such as gamma rays or blue jets or red spirits?
Yes, so there actually is another instrument called the Atmosphere Space Interactions Monitor, or ASIM. That's it's a European instrument. It's on the ISS, actually, with ISS LIS. They're not necessarily co-located, but they're both on the ISS. And ASIM does have does take some measurements in the 337 nanometers, which is more in the blue and UV type of the spectrum, whereas ISS LIS is more like near infrared. And that does provide some additional information about lightning physics, and that's one of the things we're looking at, doing comparisons between the two instruments. ASIM also does image at 777 nanometers. But yes, there are a lot of interesting spectra within lightning, and we continue to explore the relative value of each interesting emission line in terms of not only detecting lightning, but getting more information about it.
Thank you. And also, I think this question goes to Guzman. And does your enhancement technique and process comply with US limits on resolution of Earth imagery?
Yes, thank you. So we're currently offering a sub-meter resolution, but about 90 centimeters special resolution at an altitude of 500 kilometers in the visible. And our goal is to extend that to the shortwave infrared below 4 meters. Honestly, I do not know what the latest limitation imposed by the US government it is, but I thought it was more in the range of 50 centimeters. So I believe that we're okay, even though I think we have also the best special resolution in the market for this type of small cameras.
Thank you. And I think this question is for ISS-ABOVE. What is the next for ISS-ABOVE? And this question is for Liam Kennedy.
Yeah, hi there. Thanks very much for the question. You know, so the ISS-ABOVE continues to do what it's doing, but what's next in terms of accessing other Earth imagery? That's really where I'm focusing a lot of what my efforts are about. So currently, even though there's no HD that is coming from the space station, what is still available is the standard definition views. In fact, right now, this is just because I can do this, this is live from space right now. I always think that that's an appropriate thing to bring into the ISSR&D conference. Anyway, that's what I do. So a lot of what I'm doing is creating additional ways to bring in high quality imaging assets from the International Space Station. So these are a feature in a lot of science centers. So what I'm looking to work on is also to have those on-demand resources presented there. By the way, my exec summary didn't say a lot about what it was I've been doing, but the video that is going on just on my TV over here features some of the video from a 4K camera system from SEN, and SEN is one of those potentials for a 4K camera on the International Space Station. And you'll see in my presentation, it was more about using that on the Bartolomeo platform. So yeah, this video right now is from that camera system. These cameras have been in space since May of last year, so they're well proven.
Thank you so much. And Lisa asks a question that I still use the ISS-ABOVE virtually through public outreach and will be sharing globally with 3 events over the next few days. And if there is any comment that you want to make about that?
Yeah, so Lisa represents one of the many teachers and professionals who are using this in their public outreach role. You know, that's one of the key things that I created ISS-ABOVE to do, was to really support those kinds of outreach. You know, that's what HDEV has done. If you check the HDEV final report, you'll understand just the impact that having those live views available to the public has had. And, you know, all of those opportunities to let particularly, you know, students understand just what is going on in space, you know, all of that are great ways to improve support for what's being done on the International Space Station. So really, that's what that's about. Thank you, Lisa, for continuing to do that. I really appreciate that.
And this question goes to Timothy Lang. And let me start. There are a few questions. Why is it important to study lightning from space? Adrian asks.
Yeah, so there are a lot of reasons to study lightning from space. I'll talk about just a few. One, lightning is essentially indicates the presence of deep convection, which has very important implications for the atmosphere. It's a way to transport air from the boundary layer up to the upper troposphere and lower stratosphere. And so lightning tells us about that. So in fact, it gives us detailed quantitative information about kinematic or dynamical and microphysical processes that are occurring in that deep convection, namely the presence of ice and strong updrafts, that sort of thing. Another reason lightning is important is that lightning produces nitrogen oxides, and those constituents are very important for Earth's climate, and lightning is actually a rather important part of the overall nitrogen cycle. So it's important to understand globally what's going on with lightning in order to close these important budgets for various atmospheric constituents.
Thank you. And Elaine asks, can you give some new discoveries about sprites, lightning that goes from the ground up?
Yeah, so there's a couple things there that are important to distinguish. One is that sprites actually occur above the thunderstorm, up in the mesosphere, and so they're caused by essentially dielectric breakdown of the atmosphere at high altitude that gets stressed by the removal of very large quantities of charge by extremely large lightning flashes, very powerful lightning flashes that occur in these big squall lines and things like that. And so ISSIM is actually the instrument that is aimed in part at looking at sprites. And so they continue to look at detailed information about that. And then in terms of upward lightning from the ground, that's actually, I think they're referring to lightning that goes from, say, tall objects up into the cloud. And certainly ISS LIS can detect that sort of lightning, although it doesn't necessarily give you the details of what's going on with the channel. It does show if any light comes out the top of the cloud related to that lightning, it will detect it.
Thank you. And the next question is for, again, Liam. And Pritesh Tiwari is asking, is ISS-ABOVE also responsible for live question and answer sessions with astronauts?
I think what the question is related to, there are many approaches that allow students to speak live with an astronaut on the space station. ISS-ABOVE has been utilized in a lot of the ground side of that in schools that have been doing that, but those events are run by other education partners. One of them in particular is ARIS, amateur radio on the ISS, that allows students to speak live via ham radio. And then addition to that are the STEM on station type education programs where there's a live video link. That's not handled through ISS-ABOVE. Those are with other organizations, and the video link is handled by Johnson Space Center Education Group. I think they were on the STEM programs yesterday. So if you go back and look at the recordings of those, you'll find out more about that.
Thank you. Again, Lisa comments that it is very important to share the ISS. Let me see here. Share the ISS-ABOVE on a global basis through public outreach for our students to understand STEM and humanities. And she again thanks you for the support. And I think Lisa is an active user, and I think I've already mentioned that. And if you have any comments for her, please go ahead.
Yeah, so, and Lisa is also part of a program that's run by the ISS National Lab called the Space Station Ambassadors, where educators around the world can actually apply to become a space station ambassador. I think of it a little bit like a solar system ambassador that's run from JPL. It's that kind of thing. It's, you know, an important aspect of getting buy-in to all of this is on the education front. That's where I come from. So, you know, everything that could be done to support that in the many ways that education can be applied to this. So on my side, I always want to find ways of integrating all of these experiments into that kind of arena. So I've got my thoughts on how to pull some of the information from other experiments on the space station into the school environment, potentially through the ISS-ABOVE.
Again, for the viewers, please send your questions. And the next question is again for Liam. This is from Susan. And she recognizes that you have given a very great briefing, and also and she loves your enthusiasm for this type of effort. And in thinking about let me see here again. Thinking about a follow-on to HDEV for live streaming video, is there a way that commercial images can make money, or at least enough to keep operations going? And she says, I know you mentioned crowdsourcing, but is that far more than starting the payload and includes operations? And again, she thanks you for making HDEV the success that it was.
Well, just so everyone knows, the person who is asking that question is Susan Runco, who is the co-principal investigator of HDEV. So great praise from her, and just understand that it's all happened because of what she's been doing, and Carlos Fontanon, ISS Imagery Manager. So thank you so much. Getting to the question, yeah, in my full presentation, you'll see that I'm posing an idea that to create this next upgrade to HDEV, if you like, as more of a publicly crowdsourced approach. And yeah, there's a lot to be worked out, but it is certainly feasible to have both the build costs, the launch costs, the operational costs covered significantly through a big crowdsourced funded project. I've been involved with one with the Planetary Society where we got $1.4 million. And believe it or not, that would go a long way to cover, it would definitely cover the camera, plus likely the first year operational costs based on what I've seen, what's publicly available from Bartolomeo. It doesn't have to go there. It could go into other places. But another approach is potentially to have some commercial access available to those cameras as well, particularly if the camera is a pointable camera, which you'll see some of the video behind here from the SEN camera that's on an Arabsat satellite. It's certainly feasible that there would be a capability for those kinds of assets to be made available in a commercial manner. So it would sort of like be, yes, publicly available, and the plan is there that would be free, and then, but with potentially some other options. All of this is just pie in the sky at the moment in terms of precise operational details, but I think it's entirely possible. And with the number of people who are committed to this from a public point of view, and my own research and surveying done, there's a significant interest in having the public be involved in this way. You know, we're already paying tax dollars for a lot of the operational support of NASA and the ISS program, but nevertheless, there's still a lot of options there, I think, where the public would be actually delighted and further empowered to be part of that. Thank you for the question, Sue.
Thank you so much. And the next couple of questions is for Joshua Carpenter, and George asks, when do you anticipate the next phase of your investigation to occur, and what do you expect the next step to be?
Yeah, so the next phase of our investigation is to try to validate some of the crop heights that we were able to detect from ISAT-2. We know that the sensor is good at detecting both the top of the canopy and the ground. It's able to penetrate the vegetation, but we need to see, you know, what kind of error are we looking at in that crop height, and we expect to do that in the end of this year.
I think thank you so much, and I think Adrian is asking. I think you have provided that information in the full briefing, but anyhow, she's asking what are some applications of your research?
Okay, yeah. So our lab is working a lot on trying to predict crop yields as far in the future as we can. And much of the research so far has focused on small areas of land, let's say a single farmer's field or something of that nature. What we want to do now is scale up. Can we scale this up to the size of a continent? Can we determine how much corn will be produced across the United States? And to do that, we need a global scale sensor, and something like GEDI or ISAT-2 is really fitting the bill for that. So that's our main goal, is to try to predict crop yields, and crop height is one of the key determiners of yield.
Thank you so much. And Brian asks, is Purdue doing a lot in this area?
Purdue is doing a lot in the field of agriculture. Our lab is working a lot on prediction of crop yield, but as far as using spaceborne sensors on agriculture, that's pretty specific to our lab.
Thank you. Susan Ranko asks, are you selecting specific areas of known crop areas?
Yeah, so the quick answer to that is yes. The more detailed answer is that we have some fields near Corpus Christi, Texas, which we've flown using drones multiple times throughout the year. So we have good measurements of the crop height over time. So what we've done is we've specifically picked GEDI returns which fall within that field. And a GEDI return, when the laser gets to the ground, the beam is about 25 meters in diameter. So we're able to cut out that circle out of our data that we have and really analyze what is inside that circle and what sort of return should we expect. And that way we can validate what the GEDI information gives us.
Thank you. Pritesh Tiwari asks, why is it necessary to monitor crop characteristics from ISS? Can we not do that from ground?
And this kind of takes us back to the application. If we want to scale up our predictions, if we want to look at something as large as a state or a province or even an entire continent, we need something that can do a global scale, and it's just not feasible from the ground.
Thank you so much. The next question is for Rafael. Susan Runco asks, for iSIM, do you have the geolocation being calculated immediately on orbit, or is that something you determine on the ground?
Yes, thank you, Susan. So in this case, we have to do it on the ground because we had to submit our scheduling files about 2 weeks in advance. And since we were, of course, on the ISS and we had no ability actually to position our camera, and the ISS moves quite a lot. And there's also a little bit even of a time difference. So we have to do all that on the ground. But eventually, of course, we want to include it as part of the onboard capabilities on a microsatellite.
Thank you. Again, request, please send those questions. And Susan, I think another question, let me check here. Yeah. Again, this question is from Lisa to Joshua. She asks, regarding the yield of crop heights, are there any collaboration with academia or citizen scientists through GLOW program developed? And she says that she's very familiar with the Corpus Christi, Texas UAS drone certification training. And she grew up in Corpus Christi, Texas, and also in the Texas Naval Air Station. She is very much involved there. So this question is for Joshua.
Thanks. So far, we're just beginning our research, so we haven't branched out and explored many collaborations yet, but we're always interested in collaborating with other researchers, but haven't done so yet.
Thank you. This question is again goes back to Liam and Timothy. Can you share more about the ISS geolocation tool? Is that available to the public, example for students?
Yeah, so what this is referring to is something I talk about in the longer presentation. We developed some software. It's open source software. It's actually on the NASA GitHub website. You can find a link to it in my main presentation. It's a way to geolocate any camera from space, including the ISS, and it's publicly available, open source, written in Python. You need ephemeris information, so you need the two-line element information that is generally publicly available for ISS. I don't know that it's publicly available like in near real time, but it's definitely after the fact. And then you need information about the camera, and ideally you would also have pointing information. If you have some known reference points, you might be able to back out the pointing angle after the fact with some effort. But at any rate, yeah, it is publicly available for anybody to use.
Great. I plan to use it, Timothy. That's exactly. It's just a fantastic capability. I imagine because you show in the presentation the actual example of you using it with other camera resources on the station, and also with astronaut photography as well. So certainly all of the TLE information is readily available. If you go to the right NASA page, you can get really up-to-date TLE data. And my plan is certainly any camera that is launched under this potential that I'm talking about, I want as much of that data to be available in real time to the public. So, and there are several ways you can get a lot of the live telemetry is published second by second for many of the systems on board the station, including the current orientation of the station. And, so it's relatively accurate. I know you need to be a lot more accurate to get to the kind of data that we're talking about for matching a coastline to, an actual image from a camera, especially if it's video. But hey, in the world that anything's possible, that's where I'm going with this. Thank you so much.
No worries.
Thank you. Again, let me ask you questions here. Could you please elaborate on a storm scale resolution that you have mentioned in your briefings?
Oh, for the lighting, yeah, storm scale. So basically, what that means is ISS LIS's pixels is about 4 kilometers at nadir. That's the spatial resolution, which is enough to at the scale of a storm to actually map out individual lightning flashes in 2D space. So you can tell something not only, yeah, lightning occurred, but it had this particular shape. It was this big of a flash, that sort of thing. So that gives us a lot of useful information. That's what storm scale referred to.
Thank you. In regard to the frequency of lightning strikes, do you see that it is increasing or decreasing, or on an average it is the same?
Yeah, so we, TRIM LIS was up there for almost 2 decades. But it only looked over the tropics, and over the tropics there was not really an identifiable trend. Where we might expect lightning to increase is actually poleward of the tropics, in the higher latitudes, as they get warmer and that sort of thing. And that's something that ISS LIS will let us be able to answer, and it's one of the things we'll actually look at in the next year or two. Probably we'll start to look at that question.
Is this real-time monitoring?
Yeah, ISS LIS does provide a near real-time. It provides 2 data products. One is the normal science data set, which is available kind of on a daily basis, and then there is the near real-time, which is actually updated every 2 minutes. And that information is provided through the GHRC DAC, the NASA archive that is run out of Huntsville.
So is there an app that people can download on their smartphones or a computer?
Oh, for this, an app? I don't know about that. That's a good idea, though.
And I think I have a last question for you. Do you capture intra-cloud and cloud-to-cloud lightnings? Yes.
So ISS LIS is a total lightning sensor, both intra-cloud and cloud-to-ground. And that's important because it's really the total lightning that is most strongly tied quantitatively to thunderstorm processes.
Thank you. I think next set of questions I would like to ask Rafael. And are these cameras synchronized? Do you have only one camera at this time? Do you have only one camera, or do you have the shortwave also there?
Yes, it's only one camera at the moment. We just wanted to test the entire optomechanics and electronics plus the super resolution algorithm. The next one that will go also to the space station next year will have multi-spectral capability and agility to be able to trace down coastlines and other irregular structures. And then the camera capability with full visible plus near infrared and shortwave infrared will be launched in 2022.
Thank you. Is the next camera, that is the shortwave IR camera that you are planning to use, is it in-gas based or germanium based, or is it cooled or uncooled?
Yes, in-gas based, and it is uncooled, and it's remarkably very well adapted for the type of thermal environment that we are using in this camera. So that allows us to operate both the visible and the switch channel at the same time. It is quite remarkable, actually.
And I think the pixel sizes are same for both cameras.
We're doing about 5.5 microns in the visible and about 12 microns in SWID, but very much they are linked to our diffraction limited optical design so that we can sample the PSF adequately.
And again, what is the aperture size of your telescope?
It's 150 millimeters.
Oh, okay. Okay. And do you have a facility? I think you have mentioned that in your full briefing, but do you have a facility to attach an hyperspectral operation to your camera?
We do. We are very much limited at the moment by the power of the electronics. We're generating a huge amount of data. We take data every 200 microseconds and at the speed of 1 gigabit per second. But as the electronics, we're now using the system of module and the latest generation of FPGAs, and they become more and more powerful. We should be able to incorporate more and more bands. Right now we have 4, but we want actually to go all the way to 15 or 20.
And do you have any plans in the future for doing a spectropolarimetric type of imaging?
Yes, we do. And this is something that is being actually done in a very, very innovative way by a colleague of mine, Charlie Telesco at the University of Florida, in which we can actually do in the visible the full linear and circular polarimetry without moving parts. And that is very, very neat. And we will incorporate it in the camera. Yes.
Thank you. I think there is a paper in maybe 2-3 years ago in the SPI defense where we have published a spectropolarimetric imager with a liquid crystal devices and no moving parts and very compact that will provide you not only Stokes but Mueller matrices also. So in a matter of few seconds. So I think that technology is there, and you should be able to develop that for your application.
Thank you. I will check it out, and I really appreciate that suggestion.
So these few questions for Joshua Carpenter. And I think before I go into my questions, Mario Runco asks, in predicting crop yield, presumably with more crop height detections relative to ground detections, is there any consideration in the technique for detecting crop health so that yields determined at one point in time would carry through to harvest time? It seems that crop success is assumed in the technique. And this question is for Joshua.
Okay. So far in our research, we haven't investigated how the GEDI waveform might predict or be used to determine crop health. We haven't gone that far yet. So far, it's strictly the crop height. But as this research progresses, I expect that we will bring more variables into our prediction models.
Thank you. And before I go into the questions from viewers, what is the operational wavelength of your LIDAR, and is it a pulsed LIDAR? If it is pulsed, what is the pulse length of your system?
I don't have the specifications memorized right now. The GEDI, I'm trying to remember. The GEDI is a near infrared LIDAR, and the ISAT is it's like a green
Okay.
laser, but I don't remember the exact numbers on that.
And what was the measurable vertical resolution that you should be able to achieve?
So with GEDI, it's advertised to have about 15 centimeters of vertical resolution. With the ISAT-2, it's 3 to 5 centimeters.
And again, in regard to the signal processing, do you do real time or is it quasi real time?
I assume that as we develop this, it would end up being somewhat quasi real time. The GEDI, the orbits of GEDI and ISAT-2, they only go over the same spot every 6 weeks to 90 days.
And I think again, this is more about the specifications. What are the telescope characteristics at this time? Are there any plan to improve the telescope aperture size so that it can capture the resolution that you are looking for?
Yeah, that's a little beyond the scope of what I know, but I don't know of any plans so far.
Okay, thank you. And this next question is for Liam. ISS is moving at a speed of 8 kilometers per second, but the live stream we see does not look like with respect to Earth. It is not moving that fast. Can you talk something about it? This question is for Liam, asked by Preetesh.
Yeah, sure. And I did actually post an answer, sorry, into the chat for this. I wasn't sure it was going to come through. So yeah, it's a common sort of misunderstanding, just an appreciation of what it looks like in real time in space when you have a wide field view and you're looking at 400 kilometers up. You're stuck in this term of it's going at 22,000 kilometers, whatever, 17,000 miles per hour. So you just think it should, any video you see real time, the Earth should just be spinning underneath it so quick. And the live stream, like this is a recording of a live view, and this is what an astronaut would see. So some people expect that it should be going a lot faster, and in fact they're often confused. It's a common thing, so it's nothing to be ashamed about. A lot of the videos that we may see produced from some of the assets on the space station are time-lapse, particularly ones that show the ISS at night passing over cities and the aurora. They're often sped up 20 times, and that actually fits the standard way that our brains want to think about what it's like to be on the space station. That sort of fits. Oh yeah, that's how fast it's going, because that's the space station's going ridiculously fast. But anyway, this is real-time capture. This is from that 4K camera. Hopefully that answers that question, but I really appreciate the question and having an opportunity to speak to that. Thank you.
Thank you. And the last question probably is for Timothy. And I think, will ISS be able to monitor lightning in higher latitudes, 62 degrees or plus? And if so, what is the highest and lowest latitudes that lightning occurs? Antarctica, see any, or will it be a CubeSat?
And Timothy,
Okay.
we're out of time, so please, quick answer if you can.
Oh, yeah. So because we go up only to 55 degrees latitude, we can't see that high. But there was recently detected by ground networks lightning within a few hundred miles of the North Pole. So.
Thank you so much, and thank you for the panel members and for their excellent answers. And I hope this session has provided all the benefits for the Earth observing and viewing public. Thank you.
Excellent. Yes, thank you. Thanks to everybody. Liam, Rafael, Tim, Josh,
thank you.
And especially Prasad. Thank you so much. It was a great session. We really enjoyed it. And I highly recommend to anybody spotthestation.nasa.gov. Go out. It'll tell you when it's passing overhead, and so you can go out and see it go by. And then you can get an appreciation for just how fast it really is going. So it's very cool in that respect. Okay, so we're now going to take a little bit of a break. We'll be breaking until 18:30 Universal or 14:30, 2:30 Eastern Time. We'll reconvene right here. Don't leave the room for our next panel on technology development and demonstration. So we'll see you in just a few minutes. Thanks.